All right, so one of the biggest troubles that students have with this whole disk method and washer method thing is sort of visualizing what they mean, especially with the shell method. So right now I just wanted to go through and explain visually what do these things represent to kind of help you distinguish between the three. We're not going to talk about integrals. We're not going to talk about how to plug and chug through these formulas. We're just going to talk about, sort of physically, how do you make a shape out of disks or washers or shells. I'm going to cover this also in each of the videos, about shell, washers, and disk methods. Like I'll have these same pictures in each of those. I just thought it'd be helpful to put them all in one place because those videos are really long. This chapter is brutal. It's like each video is an hour long, and I just want to put these all in one place to kind of give you an overview. Or if you've already figured out how to do these for the most part and you're just trying to kind of put it all together, I really want to explain this because the shell method is the worst, and students are really confused by that. So I figured if we ease into it with disk and washer, we can explain exactly what shells are in a more straightforward way. But again, I also covered that at the beginning of the shell method videos later. So, disk method. The idea is that if we don't know how to find the volume of a sphere, because no one ever told us that formula, the whole idea of calculus and doing these definite integrals and Riemann sums and things like that is that we're going to estimate the volume of something by breaking it up into pieces we know what they look like. So when we found area of a region of a, let's say we wanted to find the area between, of this little region between a parabola and whatever this is. So what we decided was, hey, you know what, if we want to estimate area, we could break it up into rectangles. And the reason we chose rectangles instead of, I don't know, some other shape is because rectangles are really easy to find the area of. They're just the width times the height. So we just figure out the height and width of this rectangle and add it to the height and width of this rectangle and add it to the height times the width of this rectangle. If you add up all these rectangles, each of which is the right length to fit nicely between the curves, then add up all those rectangles, you'll end up with the total volume. Sorry, the total area of the region you're curious about. And it turns out that if we use an integral, the more rectangles you use, the more accurate it was using a Riemann sum. But we figured out, or somebody figured out, and we were told and learned how to do that if you use an integral, that's the equivalent of breaking this region up into infinity rectangles. And therefore, your approximation will be exact. So it's not an approximation anymore. If we just added up these rectangles manually with Riemann sums, it's not exactly right. But if you use an integral, bam, infinity rectangles, zero error, you get the exact area. So what we're going to do now is sort of fool an integral into taking volumes for us instead of areas. So each of these little rectangles in the disk method, what we're going to do, we can't use this region quite because it doesn't have a square bottom, but for disk method you have to have a region that has a flat side, and that flat side has to be along the spin axis. Because disk method cannot handle holes through the center of the solid. The solid has to have no holes in it. But if you can use a disk method, what we're going to do is we're going to basically take a sphere. Like this particular example, if you want to find the volume of a sphere, you could break up the sphere into a bunch of flat pancakes. And just like we match these rectangles to be the right size to sort of follow the outlines of the region we're trying to do, we could do the same thing with these disks to make them add up nicely to a sphere. Alright, so that's the disk method, and obviously, like I said before, we can't have any holes in it. Now if you want to know how to actually execute the disk method and do the integral and use the pi r squared formula and all that, you'll have to do that. You'll have to watch the video about the disk method. So what is the difference between the disk method and the washer method? Well, the washer method, these are basically just a bunch of disks, except they've got holes in the middle. And as we showed in the washer method video, it turns out that's really great because that means you can stack up washers to create things that have holes in them. So you don't just have to do spheres and stuff, you can do things that have holes. I've said the word holes about 20 times now. Point is though, and then why do we pick washers? Like why not some other shape? Well, it turns out a washer has a lot in common with a disk. The area of a disk is just pi times the radius of that disk squared, because that's just the area of a circle. And then we'd multiply it by the thickness to get the volume of the disk, which is usually dx. But the area of a washer is just that same amount of volume, that same amount of area, but then we're going to take away the area of the hole. So if you want to find the area of just the yellow part, for example, on this top one, you just take pi times the outside radius squared and subtract pi times the inside radius squared. And dx, as you'll see in that video, in these, just like we did in area, dx is what we're going to use for the thickness of whatever disk or washer we're looking at, that little thickness right there. And of course, when you take an integral, technically that's getting down towards 0, because we're going to try and pack infinity of these washers into this shape. So obviously they're going to have to be really, really, really thin in order to fit infinity of them in, just the size of this bundt cake. But anyway, so washers are really similar to disks, very similar formula. The only difference is we have two radiuses to worry about, the inside and the outside. And then, so these are pretty straightforward, and it seems like most students, that you prefer the washer method. So disk, you really can't use very often because almost every question you'll ever get in calculus will have a hole in the middle. So you're pretty much going to be stuck either doing washer or shell, and students hate shell. Washer method, it uses pi r squared. You've been seeing that, pi r squared, area of a circle, you probably saw for the first time in 4th grade or something, or 7th grade at the latest. So everyone's really comfortable with that, and I think that's why students like the washer method. However, the shell method, it turns out, is actually more useful. Like, the harder problems get, the more likely that shell will turn out nicely and that washer will be a mess. So it's kind of a shame that people dislike shell so much. So let's just take a look real quick at what the heck the shell method is. Now we're going to look at 2 examples on this one just because it is so complicated and weird. But the bundt cake again, of course, and the sphere. So let's just look at what the shell thing means. Like, why is it called the shell method and stuff? Well, first of all, it should not be called the shell method. It should be called the tubes method, or pipes or whatever, because really what we're looking at here is a bunch of tubes. These are all tubes that are nested inside of each other. So if you look at this sphere right here, this is actually very similar to the drawing I just showed you a second ago for the disk method, where we sort of simulated a sphere by making a stack of pancakes. Except this is a little different, so even though the end result looks the same, the sphere looks kind of similar. In fact, it is a bunch of pipes inside of each other. And they're different lengths and different radiuses, right? So if you wanted to, you could go to a hardware store like Home Depot or something, and you could go to the plumbing section and find a bunch of pipes that just get slightly larger ones and larger, so they just all fit inside of each other really nicely. So like one barely fits inside the next one, which barely fits inside the next one. So you can imagine if you took 10 centimeters of each of those sides of the pipe and put them all inside of each other, you pretty much end up with a solid brick of steel, or whatever the pipes are made out of, or plastic. So in the same way, so basically what you just did was you created a cylinder, a solid cylinder of plastic, from a bunch of nested or interlocking tubes. And that's what we're doing with the shell method. But of course, if we want to make a shape other than a cylinder, so what we could do is, if we just nested all the tubes and they were all the same length, we'd end up with a cylinder. And once you spin around the spin axis, it ends up over here. So at that point, you just have a solid brick of plastic. But what if you want to make a shape that's better than that? Or more accurately fits the problem you're working on, like the sphere? Well, then you're going to want to make, like in the case of a sphere, this inside one, the red one, is the longest, because that's sort of like the maximum dimension of the sphere. It goes all the way across the sphere. But then as you work your way out towards the outside, going to the bigger and bigger diameter pipes, they're going to be shorter and shorter just in order to follow this contour of the sphere. But you can imagine making this, if you went to Home Depot, you bought all the tubes, you put them inside of each other, you could almost take like a saw, and sort of like saw it down to where it formed a sphere. And that's actually something I considered doing. It's just so much work, but I thought it'd be a really good illustration. I decided to cook it up in Illustrator instead. But the point is that you can make almost any round shape you can make out of nested tubes and just make them different lengths to follow the contours. Obviously it's a little bit different, a little bit harder to visualize this than a stack of washers or a stack of disks, but the concept is the same. So the sphere, somewhat obvious, but let's take a look at this one. So here we've got the bundt cake that I keep using on these revolved problems, but this one's less obvious what's going on. But once again, we looked just a minute ago, we looked at a drawing very similar to this. There was just a stack of washers. But again, just like with a sphere, if you pull this thing apart, it turns out what I really did was I interlocked a bunch of nested tubes that are all just barely small enough to fit inside the next one outwards. So we go from big diameter to small diameter. They're all the right shape to follow this contour. So we got the red guys on the ends. So this one obviously is the one you're seeing right here, but then this little red guy is the one that's deep down in here on the inside, because it's the smallest diameter. And the shape is flat on the bottom. So if you just took all these tubes in this pyramid on the right and just set it down so they all went inside of each other and settled down to the table, you'll get, see how this is flat on the bottom? You get this exact contour. So this is the region. I've got the spin axis here. So here's the region that you would be given on your problem, and that's like, you know, they tell you, hey, take this, there's maybe an upside down parabola or something. So the region they would give you is, hey, they'll give you the, you know, the equation of this parabola, which is an upside down parabola, and then they'll say, hey, the bottom of this region is, you know, y equals 2 or whatever. So here's the region, and then they'll say, find the volume of the solid of revolution of this thing around this axis over here. So because there's a gap, that means there's going to be a hole in the center of this bundt cake thing. But this shape is a cross-section of anywhere you cut this bundt cake, you're going to get that cross-section. So that is what shells are all about. They're interlocking. And I know it seems really weird to do this, and you don't see why this would be a good idea, because you've never in your whole life probably had to take the volume of a piece of tube. But it turns out that since we're in calculus, these tubes are really thin. They're dx or dy thick, the wall thickness of this tube. So what happens is if you take this, you know, you probably have no idea how to find the volume of a donut-shaped ring thing, but if you just cut it with a knife or scissors or something and unroll it and just flatten it out, you end up with a long strip. And what is the size of that strip? Well, let's see. The height of the tube, this little height, h, or, you know, for a bigger one, it's like this height, the height of this gold one, let's call that h. That's this little dimension, right? So after you slit it and unroll it, h is just sort of the right edge of the rectangle. And what do you know? We've been using rectangles a long time now, right? We use rectangles for area also, because they're easy to find the area of. So h is h, and then what's the base of this rectangle? Wasn't that just the circumference of the original ring? Because before you unrolled it, that ring basically just made a circle of radius r. And we were familiar with r because that's what we used in the disk method also. So this bottom edge, this whole base, is just 2 pi r, because that's the circumference of a circle. And then of course its thickness is what I just mentioned, is dx or dy or something, just like in the disk method and washer method. So basically if you want to know the volume of this rectangle thing, it's just base times height times thickness. The base is 2 pi r, the height is h, and then the thickness is dh. So the volume of this little rectangle is 2 pi r times h times dx for thickness. So now you kind of see, oh, wait a minute. If you've already seen the shell method equation in class, this is the shell method equation. If you just throw an integral on the front of this, bam, that's your shell formula. So all we're doing is, instead of breaking up a round object into flat pancakes that sort of sit on top of each other, we're breaking it up into tubes that nestle inside of each other. And because of that, and here's the big trick, is that the reason this works for some problems that washer method does not, is you'll notice these little rectangles that we're sort of breaking things up into are representative rectangles. They're parallel to the spin axis. So that's the biggest difference in the execution of a washer method versus shell method, is that in shell method, the representative rectangles are parallel to the spin axis. That's how you get a tube. But then in the washer method, they were horizontal or perpendicular. So if I was doing the washer method on this upper drawing here, for a vertical spin axis, you'd have a horizontal little rectangle. And that just makes things different. You know, for this region spun around this vertical axis, you'd have to use dx for the washer method. I'm sorry, that's dy because it's vertical. But then you'd be using dx for the shell method. So basically, if you know both the shell and the washer method, you can walk up to a region, you know, problem, look at the region and say, hey, which one's easier to use, dx or dy? And then once you pick one of those, you just pick the corresponding method. So in this case, if it's a vertical spin axis, and it looks like it would be easier to use shell method, or it looks like we want to use a vertical rectangle, then it's just automatic. If you have a vertical rectangle, vertical axis, that means you have to use shell method. If you wanted to do a horizontal rectangle, you'd have to use washer method. So hopefully that goes towards explaining what the heck shell method is. Everyone likes washer. Everyone hates shell. But once you get really good at them, if you sort of learn shell at the same time as washer and therefore don't have a preference, shell method's a little weirder, but it's actually easier to plug and chug through. So if you watch that video, it's a really long video, it's an hour long, but by the end of it, we're just plugging and chugging like champs through shell problems. So I would encourage you to check that out.